In this problem, we are given a system of charges and points in which two charges Q1 and Q2 are placed on opposite sides of the origin and equal distance from the origin. And the charges are the charge of an electron but have opposite signs. And we're also given Coulomb's constant and the charge of the electron and the distance between one of the charge to the origin. And since we know that they are equidistant from the origin, we know both their distances are 2 nanometers. So the problem we are asked to do is to find the magnitude and direction of the electric field at point P. So before we do any numerical calculations, it is more beneficial to analyze the direction of the electric field at point P, because due to the symmetry of the problem, we can make the calculations easier. So first, we know that a positive charge will have electric fields coming out of them towards point P, and by definition, a negative charge will have electric fields coming towards them. So when that's the case, when we break down the components of the vectors, we find that in the x directions, the vectors will add up, and in the y directions, the vectors cancel. And so algebraically, we can write this as E1y equals negative E2y. And what this means is that the total electric fields in the y direction would be E1y add E2y, which is negative, equal to 0. And the x component for the x components, we have E1x equal to E2x in magnitudes, and since they are both in the same directions, they have the same signs. And when we add them up, we get 2 times E1x or 2 times E2x, which would essentially be the same since both the x components are the same. So to find the magnitude of the total, magnitude of the electric field on point P, we need to add both the directions of x and y, which we know for the y component it is 0, and the x component is 2e1x, or equivalently 2e2x. So what this tells us is that the direction of the electric field at point P will be entirely in the x direction, and in terms of magnitude, we can solve for the x components alone and double whatever we get for one of the components and get the total electric field. So we're going to use Coulomb's law to do that. Coulomb's law says force equals kq1 q2 over r squared. And since q1 equals q2, we can call them q. So it would just be kq over r squared. And to find the electric field, we'll have the Coulomb force divided by q, and that leaves us with kq over r squared. So if we look at all the variables, we know we have the charge we need to plug into the equation, as well as the Coulomb constant. what we are missing is r, and r is the distance between the charge and the point. And to do that, we're going to use one of the trig functions. So we're solving for this component, which is the hypotenuse of a triangle, and we know d, so we have the adjacent side of this angle and the hypotenuse of the angle. And since this is an equidistant triangle, we know that all the angles are equal. So in a triangle there are 180 degrees, and so when divided by 3, that gives us 60 degrees for one of the angles. So let's call this theta, and theta equals 60 degrees. And to solve for r, we'll have r, or I should use the trig function first. Cosine of 60 degrees would equal to the adjacent side, which is d, over r. So r would equal to d over cosine 60, and we know from 30, 60, 90 triangle that cosine of 60 is 1/2. So we're left with r equal to 2d, and d as given is 2 nanometers. We'll multiply by 2, we'll get 4 nanometers. So now we have all the variables that we can plug into the electric field equation. But before we do that, we need to notice the units are not the same, because the Coulomb constant is in newtons, and that is essentially meters per second squared times kilogram. So when we have nanometers, we can't just simply get an answer, we need to convert nanometers. So we'll have 4 nanometers, so we'll convert nanometers into meters. So 1 nanometers equal to 10 to the negative 9th meter, so 4 times that is 4 times 10 to the negative 9 meters. And now we'll be able to plug everything we know into the electric field equation. So we have the Coulomb constant, which is 8.99 times 10 to the 9th newtons, times the electric charge of an electron, or just the charge of an electron. So now when we divide it by r squared, we'll have 4 times 10 to the negative 9th meter squared. And now we'll be able to plug into the calculator and solve whatever the electric field is. So the electric field at point P, due to one of the charge in the x direction, happened to be 8.99 times 10 to the 9th newtons per coulomb. And we need to solve for 2 of them to find the total electric field. So this is E1x, and for EX, for the total EX, we have 2 times E1x, and that would be 1.798 times 10 to the 8th newtons per coulomb.